Okay. We're going to continue talking about metabolism. Don't worry about the mess that I wrote on the board yet. Okay. We will get to this. We will get to this. But in many ways, this on the board, that's everything. That's the entirety of all of the complicated stuff that y'all are going to have to know for the test. This shows all of it. And it's happening right now inside your body. Okay. We're going to get to this in a few minutes. We're going to start off by finishing up talking about our immediate phosphagen systems. Okay. And how that works, which will hopefully prep us for a little bit of what's going on. Okay. We ended the other day talking about the creatine phosphate pathway. Okay. Now, do we all need to stand up and do squats for about 30 seconds and really stimulate and then deplete our creatine phosphate pathway?
I think we're good.
You think we're good? Matt, you wanna? Matt's like, I want to squat. Okay. All right. Go for it, my man. So, how long can this last? Okay. Anybody? It's creatine, yes. Anybody timing him? I'm just gonna guess. It's been like 10 seconds. Pardon? See if he can go the rest of the class. He might be able to. Oh, he's getting motivated. He's putting his earbud in. Okay. All right, Matt, you can stop. You can stop. Okay. Thank you, though.
We're all waiting.
Matt did this for you all. This is our primary immediate source of energy. You start doing muscle contractions. After like one contraction, all the stored ATP in your muscle is gone. You have all of this ADP now floating around in your muscle. So we need to turn it back into ATP. So this is one of the primary initial ways that we're going to do that. You have creatine phosphate floating around in your muscles. There's an enzyme called creatine kinase also floating around in your muscle. This is the fun part of everything. Everybody stand up. Okay. This is the best way I can think of to illustrate this particular concept. Spread yourselves out just a little. Now, close your eyes. Close your eyes. Okay. Spin around in place like 3 times. Now, eyes closed, no cheating. Now, just walk until you bump into something. Okay, stop. Stop. Many of you bumped into a chair and things, okay? So, I want you to, again, close your eyes. Okay? Shuffle sideways until you bump into someone. Very slowly, very gently, very light. Okay, stop, stop, stop. Okay. Now, if I wanted to make it more likely that you were going to bump into someone or something, what should I do? More people, Mallory says. Okay. More people? If there were more of y'all in the room, would it be more likely with your eyes closed if you walked around and bumped into somebody?
Yeah.
Okay. All right. Y'all can sit down. This, what you all just did.
Looking for that.
Okay. What you all just did is exactly what happens inside every cell in your body for essentially every reaction that takes place. Okay. It is all random chance because things exist in proximity to each other. You have floating around in a muscle creatine kinase. You have floating around in your muscle molecules of creatine phosphate. they will, at various points, bump into each other. You also have floating around in the muscle as you begin to exercise ADP. So when ADP bumps into or gets very close to creatine kinase and phosphocreatine, this molecule, the creatine kinase enzyme grabs the phosphate off of here and hooks it onto ADP, and we make ATP. And this happens by random chance, okay? By random chance. Still blows my mind, okay? Random chance. We are alive because things like this just happen, okay? And so, one of the things, and this is going to be important not just for this reaction, but for everything else that we're going to talk about. Metabolism is driven by changes in the probability that these random molecules will bump into each other and then drive a reaction in a certain direction, okay? So, if I want to make this reaction more likely to happen, just like if I want to make, with you guys with your eyes closed, more likely to bump into someone else in this room, okay? If I said that half of you were molecules of creatine phosphate, a third of you guys are molecules of creatine phosphate, a third are molecules of creatine kinase, and a third are molecules of ADP. If I want to make it more likely that the three of you all will bump into each other roughly simultaneously to drive our reaction, what should I do? How do I make that more likely to happen?
Increase the number and like all of us.
Yes, increase the number of all of those things. Very good. Okay. And so what happens with metabolism, and this is the big thing, guys. If you can get this, so many of the other things we're going to talk about today and Friday will make way more sense. Okay. The one thing that changes here, and that's going to change in a lot of our other ones later on, is the concentration of ADP. Okay. At rest, you have some stored ATP in your cells. Okay. ATP, when it bumps into these things, does not drive this reaction. But as we begin to exercise and we deplete ATP into ADP, this rises and it helps increase the chances then these things are going to bump into it. By increasing the concentration of one of the things that we need, it drives our reaction to the other side. Okay. I apologize, I apologize for having to talk about chemistry again. Okay. But this is freshman chemistry. This is biochemistry. This is one of the most prominent things that works and keeps us alive in physiology and functioning. Okay. Is if you increase one side of an equation, it drives it in the other direction. So we do this. Okay. This reaction is fast and very sensitive to changes in ADP. It's fast because there's one enzyme, right? One enzyme, boom, and it goes. Okay. That's how this is going to work. What I illustrated, the same thing is going to happen in every metabolic equation. Okay. In every metabolic equation. Increasing the concentration of ADP inside of a muscle cell, because we're using that ATP to initiate contractions, to resequester calcium, to repolarize our membranes, increasing ADP essentially stimulates every metabolic reaction to start going. Okay. So it's increasing that concentration. And what it does is that's a necessary thing. By its concentration going up, we're putting more of you guys in this room. So there's more of a chance that you're going to randomly bump into this. Does that as a concept and an idea make sense? Okay, because all of metabolism is driven by that. Matt.
I just heard someone ask one this earlier, so I was just kind of curious.
Mhm.
Is there a way to increase surface area of ADP?
So I can inject ADP into your muscle. And that can be a good thing. And that would drive a reaction in those ways. If we increase your creatine consumption, we can make the creatine phosphate molecules go up in about 80% of people. But the problem is you can have more creatine phosphate, but until there's more you need all three of these things up. And this is the one thing that actually changes. We can make this go up so we've got more, so it takes us longer to deplete. But this is the main thing that drives it.
Gotcha. I was just like, is there a way to actually like make the individual ADPs bigger?
Oh, no, absolutely not. No. Adenosine it's just as big as it is, right? And adenosine functions as that scaffold, and you hook a phosphate and a phosphate and a phosphate on. And so no, there's not.
Yeah. Curious about that.
Yeah. An interesting idea. Okay. All right. So I think we've covered most of the stuff on the next slide, except for the stuff at the very end. Okay. So many of you guys have had the experience, right? You did something that was very high intensity. You felt like you had some level of fatigue, and then you rested for a few minutes, and then you did it again, right? I did a set, right? Wednesday. What are the bros doing today? Is it shoulder day? Biceps, back and biceps today. All right, let's get it. So you do a set of curls, right? You go to failure, and then you rest. Then you go again. Okay. How long do we tell people they should rest in between sets of doing weights? 1 to 3 minutes. Okay. If you guys in your other classes did a 1 rep max test where you did maximal strength one time and you did multiple attempts, remember how long you were suggested to rest in between those? Okay, 5 is usually by ACSM guidelines, 5 is what they suggest. Okay, where do you think we got those numbers? Where do you think those numbers came from? Nathan?
The rate that it takes your body to turn off ADP back to ATP.
Okay. You're close. You're close. Okay. Those numbers for the rest period are derived from how long it takes us to remake creatine phosphate after you've stopped exercise. Right? Matt was doing squats. He depletes his creatine phosphate. It's gone. He has creatine floating around in his muscles still. You don't make creatine phosphate back again until you stop and you drop metabolic rate. Okay? Because we use energy to put a phosphate back onto creatine. And the energy that we use comes from ATP made in the electron transport chain. It comes from aerobic metabolism. Okay. This process is called the creatine phosphate shuttle. Okay. But I run, I squat. Creatine phosphate depletes. I got to stop. As soon as I stop and metabolic rate drops, I start making creatine phosphate back. We can put you in an MRI machine. We can do magnetic resonance spectroscopy, and we can track how quickly creatine phosphate levels recover. Okay, how fast they recover. And I'll show you guys a picture of what that looks like. But it uses ATP made in the mitochondria. And after about 5 minutes, you've got about 99% of it back. Okay. Has a half-life of recovery somewhere between 30 seconds to 90 seconds, and you've got half, and then another 30 seconds, and you've got another half, right? So now you're at 75%, and half, and half, and half. It goes out like that. Okay. Recovery between sets is governed by how well aerobically trained you are. Okay. By how well aerobically trained. A cross-country runner will recover faster in between doing a set to failure of resistance training than a person that is not very well aerobically trained. Okay, it's a really, really important concept. And so it looks like this. And you guys don't have to know this anyways. You don't have to really, you're not gonna be asked to recreate it. I just wanted to show you guys what it looks like, okay? This is person in an MRI machine. You have them exercise like Matt was doing, squat, squat, squats. They're not squatting in a magnet, right? They're doing, it's usually plantar flexion or something. You're doing this, you deplete creatine phosphate, it falls, we stop exercising, and then it recovers back. And you can graph this, you can fit a curve here, and we can mathematically determine how quickly this is gonna come back. Okay? Same thing here, we depleted it farther, right, and you see that it's gonna come back. So the farther you deplete it, the longer it takes to come back in those particular ways. And the shape of this curve will be different depending upon how well your mitochondria work. But this is what is happening. You sprint and you stop, right? You lift weights and then you rest, okay? So next time somebody looks at you funny because you're taking a break in between sets and you're looking at your phone, right? You're looking in the mirror, you're checking everything out, whatever's going on. I'm just letting my creatine phosphate resynthesize, right? Physiologically, I'm just doing the right thing here, man. That's what we're doing, okay? That is how all of this works, okay? So you do this and you don't rest long enough, it doesn't all come all the way back. And so then you do your next set and you start off with less creatine phosphate than what you had on the set before. So guess what happens? Can't do as many reps, right? Can't do as many reps. But you can't sprint at the same speed for the same amount of time. Okay. And so this is one of the things that goes on here. Okay, Joe, you had a question?
Based on, is this based on intensity, like how heavy the load is, or is it based on like how long?
All about intensity. Well, it's an interaction. It's mostly about intensity, right? If intensity is low, we don't really have to use a lot of creatine phosphate because we can make enough ATP from over here that we can sustain that level for a while. To use those immediate systems, it's the start of exercise, and once you clear about 30 seconds or so, right? If it's enough that you can make it from here, then that will kind of get tamped down. Or basically it's been so high, you've had to use it and it's gone. Okay. You do not recover creatine phosphate until you stop exercising. So you're not like jogging and like, well, I depleted my creatine phosphate. I guess I've made some back. You probably make a little bit, but for the most part, once it's gone, it's gone. Because all that stuff coming out of the mitochondria is getting used elsewhere. Okay. Does that make sense, guys? Okay. We get really desperate, we do something called the myokinase reaction, which is the same idea. There's a different enzyme called myokinase, but basically if two ADP molecules bump into each other, and then they bump into the myokinase enzyme at the same time, we pull a phosphate off of one of the ADP molecules and you make ATP and AMP or adenosine monophosphate. So we can make a little bit of extra that way. You don't have a lot of myokinase. We don't do this very often. It's only during very, very, very intense exercise that is very kind of short duration. Okay. So again, you don't have to know these numbers. I just wanted to try to give you guys something to relativize how much energy we have available in the phosphagen systems compared to each other. Okay. So here's what they're essentially calling total kcals per muscle mass. Just look at these numbers relative. You have stored ATP in your muscle of about 2. Don't even worry about what the units are, 2. Most people have about 4 to 5 times that much energy stored in creatine phosphate, and you have even less, right? You have about half as much as you do stored ATP available from the myokinase reaction, okay? So when you need energy right now, we use this. It gets depleted. That makes ADP, which drives us to use this, okay? And if it gets really, really low, then we're also going to do a little bit of this. And once all of this is gone, if you can't make enough ATP from your other pathways, you've got to stop exercising completely, or you have to slow down. You've got to not go to the same power output. You got to slow down. You got to walk, whatever it's going to be, because once this is gone, it's not coming back until the rest. Okay. Okay. We've done the easy part. Now it gets more complicated. And I'm sorry about that, but this is the way that it is. I just want you to know that if you'd been in our major a year and a half ago, that our previous department chair, when he taught this, would have made you memorize every step in glycolysis and all the enzymes that do every step. And I'm going to be kind and only make you learn this. So I feel like you guys should appreciate that about me right now, right? The road not traveled, right? So you guys should all roll your eyes at it and be like, okay, so let's talk about glycolysis, okay? This is probably, to me, in some ways, the most conceptually difficult thing for us to understand about metabolism. And a lot of it, to me, has to do with how it has been presented to you guys in the past, okay? I told you guys on Monday that you've mostly been lied to about how metabolism works. It wasn't a nefarious lie. It was just to try to make it simpler for you guys. We've also lied to you in some ways about what happens at the end of glycolysis, okay? From a purely biochemical standpoint, glycolysis is taking a molecule of glucose, breaking it down, which we call oxidation, oxidizing glucose all the way down to a molecule called lactic acid, okay? To a molecule called lactic acid. And in doing that, that breakdown helps us make some ATP, okay? It helps us make some ATP. We make more ATP doing this than we have available from stored ATP or creatine phosphate or myokinase. So it's beneficial in that we get more energy. Okay. Problem is that lactic acid causes problems. Okay. Not really the lactic acid, it's really it's the acidic part, the hydrogen on there causes some problems for us. So we're going to talk about that. Glycolysis occurs in the cytoplasm. Okay, so here we are in a muscle cell. Some of you guys are molecules of glucose. You got your eyes closed. You're just wandering around until you bump into something. Okay, and then that gets you changed into something else, which then bumps into something else, and boom, 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 until we finally work our way all the way down. Okay, what we start glycolysis with is glucose. Okay, it is important to understand that glucose has 6 carbons. Okay, 6 carbons. Sorry, it's mild organic chemistry, but it has 6 carbons on it. Okay, that's going to be important. We're going to take that molecule of glucose and we're going to break it down all the way down to something called pyruvate or pyruvic acid. We're going to make 2 molecules of that because they each have 3 carbons. Okay. In the process of breaking glucose down to pyruvate, it will cost us some energy. Okay. But then we're going to get some energy back. Right. And what happens in these initial steps is going to be governed by where did the glucose molecule originate from? Okay. If the glucose molecule that gets into your muscle cell arrived there by coming from your bloodstream, it comes out of a capillary from the blood. That molecule of glucose arrives at the muscle with no phosphates on it whatsoever. The first thing we do when we bring a glucose molecule in is we use an enzyme called hexokinase and we trap it in the cell by hooking a phosphate molecule onto it. But that costs us energy. Okay? We got that phosphate from ATP. We now have a molecule called glucose 6-phosphate. Okay? Glucose 6-phosphate. Once we have glucose 6-phosphate, we're going to actually stick a second phosphate on there and make glucose 1,6-bi or bisphosphate, and then we're going to do some other things. Okay, but blood glucose from the blood, we're going to have to put in 1 phosphate here, 1 phosphate here, so it costs us 2 ATP. Glucose that comes from glycogen in your muscle already has the first phosphate on it. So it enters into glycolysis here. We already are gonna enter from glycogen with one phosphate on, so we get to skip this step. So a molecule of glucose that comes from glycogen only costs us one ATP when it enters into the system. Okay. As we move down to pyruvate, we're going to make 4 molecules of ATP. So if we put 2 in and we make 4, we net how many? 2. If we put 1 in and we net 4, how many do we make? 3. Okay. So where the glucose originates from determines how much ATP we make just from going from glucose to pyruvate. Okay. Just going from glucose to pyruvate. We get 50% more energy from glucose coming from glycogen. Okay. So you guys could likely imagine a scenario whereby preferentially then it's better if we get the glucose for glycolysis from muscle glycogen. Okay. And indeed, that's where we're going to start by trying to do that. Okay. So that's what happens. But it's coupling energy from the breakdown of glucose. I'm only going to want you guys to know basically these 3 or 4 steps. There are many other steps in this reaction. I think there's like 13 steps in this reaction. Okay. So imagine you are in here, your eyes are closed, you're walking around. You have to bump into 13 different people. Okay. In order to go from being a molecule of glucose all the way down to the end of all of this. Okay. Whereas if it's creatine phosphate, 1, right? You got to bump into the enzyme, but it's a 1-step deal. This is many, many steps. Because of that, it's slower. Okay. It's significantly slower. And so that is mildly problematic for us when you're doing high intensity exercise. Okay. Because it's slow. It may take us a little while to be able to get this extra energy. But in comparison, you're making 2 or 3 ATP when our other pathways make 1. So you're getting 100% or 200% more energy out of this. So it's good because we get more energy, but it's slow. Okay. The other problem, and we'll come back to this later on, is that glycolysis is good because we make more energy. But the problem is when you make lactic acid, that the hydrogen on the acid messes everything up in cognition to contraction. Okay. A drop in pH or a more acidic pH inhibits, you don't have to notice that, but it inhibits the function of the myosin ATPase. It inhibits calcium release from the sarcoplasmic reticulum. When your muscles burn during a bout of sprinting exercise or weightlifting, that hydrogen is stimulating afferent nociceptors or pain fibers that make it burn. That signals into your spinal cord and your brain. It hurts, and you're like, shut it down. I don't want to do this. Okay? It messes everything up. So there is this negative feedback loop potentially where if we make too much, it will shut everything down. Okay? It'll shut everything down. Okay. So what I've basically done with this particular graph or this particular cartoon from the book, I have attempted to recreate here. Okay. This is the bare bones of what it is that I want you to know. That you have blood glucose out in the blood here, glue is in the muscle, it comes in, we use the enzyme hexokinase, we put a phosphate on. Glycogen, we break glycogen down, it enters as glucose 6-phosphate, and then both of those will try to take it down to pyruvate, and potentially we make lactate or lactic acid, or we're going to do something else with that pyruvate that we'll probably end up talking about on Friday. Okay. Here's a picture from a textbook that is older than probably almost all of you in this room. This is from my biochemistry book from 1999, right? So what you see here is something called the Embden-Meyerhof pathway. And that is basically glucose to pyruvate. Okay? I want you to know glucose, glucose 6-phosphate, and pyruvate. That's it. But this is going to capture where it comes down, 6 carbons, break in half, 2, 3 carbon molecules, switch, down here to pyruvate. Okay? It shows where ATP goes in here, and ATP comes out here and here. Shows where we grab some electrons here. And it's also going to show you guys that there's an enzyme that runs every one of these steps. Okay? I want you to know this enzyme, and then the twos that are going to drive us from where pyruvate goes. So the initial enzyme is called hexokinase. Takes us from glucose to glucose 6-phosphate. The other one that's probably even more important is this one here, called PFK, or phosphofructokinase. Phosphofructokinase. This is the one that puts the second phosphate on. This enzyme is the most important one in glycolysis because it's what we call a rate-limiting enzyme. Okay? This is the slowest step in the entire pathway. Okay, the slowest step. You all have that friend, or maybe you are that friend, that you're getting ready to go somewhere and you're the slowest person to get ready. You can only get out the door as fast as the slowest person can get ready. They are the rate limiter in how quickly you can get out the door. You want to guess in the Black household who the rate limiting person is? It's always the 5. Okay. It's always the 5-year-old. Or the basset hound that likes to hide under the car because she doesn't want to go get in her crate. So this pathway can only go so fast as PFK will turn fructose 6 into fructose 1,6. Okay. You don't have to know this stuff. I just want you to know that that's the rate limiter. Okay, that's going to become important later on. Okay. So the big thing with glycolysis, glucose goes in, we get to pyruvate. And then everything after this is where you guys have sort of been lied to. Okay. Where you've sort of been lied to. And I'm going to lie to you again, but I'm going to be nice about it. I'm going to explain to you why I'm doing that. Okay. This is the same pathway. The ATP part is a little bit more. This is the one from the book, if you care. Okay. All right. So I've sort of written out what we've already talked about. The thing about glycolysis that is really, really important and is also the most difficult thing for us to grasp is what matters at the end of the day is what happens to the pyruvate. You take the glucose, we oxidize it down to 2 molecules of pyruvate, but now, up until now, all of that glucose, everything goes to pyruvate. It's very simple. The same thing happens. When we get to pyruvate, though, okay, we become a Robert Frost poem. Like 3 of y'all got that joke, right? That's my liberal arts education coming back to do things, right? We become the road not taken, the very famous Robert Frost poem, right? 2 roads diverged in a yellow wood, right? And all of this. When you get to pyruvate, the pyruvate can either go to lactic acid or it can get taken into the mitochondria and go into the Krebs cycle. All right. There are 2 potential fates of that pyruvate. And where it goes matters a great deal. Okay. Matters a great deal, both for how much ATP we can end up making and for whether or not we're going to be able to continue having these pathways to run. Okay. And this is where I feel like you guys have likely been lied to an extent. And I'm going to show you what that lie looks like. Okay. So, as I've written here, as some people will call it, there is what we call anaerobic glycolysis, which is glucose to pyruvate and then pyruvate into lactate or lactic acid. Okay? Anaerobic metabolism. No oxygen, right? Anaerobic glycolysis. Others may say there's aerobic glycolysis where it goes to pyruvate, and then the pyruvate goes into the Krebs cycle. It gets turned into something called acetyl coenzyme A. We make some carbon dioxide. Yay, that's what we're breathing out. Goes into Krebs. We make some more carbon dioxide. We steal a bunch of electrons. We make a shit ton of energy. Okay. The lie is that glycolysis is always anaerobic. Okay. There is no anaerobic or aerobic glycolysis. Glycolysis is anaerobic in the most technical of senses. The fate of pyruvate is either anaerobic or aerobic, if you want to look at it that way. Okay. And the anaerobic fate is pyruvate gets made into lactate or lactic acid. That is driven by an enzyme that I want you to know called lactate dehydrogenase. The aerobic fate of pyruvate is to be made into acetyl coenzyme A and then go in the Krebs cycle. That is driven by an enzyme called pyruvate dehydrogenase, or PDH. And so where the pyruvate ends up is the important thing, and is actually the conceptually complicated thing to understand. Right? Okay. Everybody stand up. We're gonna do one more illustrated thing to make sense. All right. I want right down here in the middle of the room, okay? Nathan, you guys this way, you guys that way. Go. Switch over to the side, please. Okay. All right. Now, here's what we're going to try to do. Okay. Let's do this. We'll just take our first 5 folks. Okay. So you guys come with me. You guys are going to be enzymes, molecules of pyruvate dehydrogenase. So sort of spread yourselves out over here a little bit. Okay. Then from here, let me get Stacy, Mallory, you guys come here. Okay. Y'all come stand right over here. You guys are lactate dehydrogenase. Lois, you stay for a minute, Bubba. Here. Okay. All of the rest of y'all are going to be pyruvate molecules. Okay. You're going to be pyruvate molecules. So we have 5 PDH molecules, 2 enzymes, 2 lactate dehydrogenase enzymes. Okay. What is the most likely thing to happen if I have every one of you pyruvates close your eyes and try to walk down here through? Who are you most likely to bump into? The pyruvate dehydrogenase. Okay. All right. So let's start with this. Okay. I want my first 3, okay, here, and my first 3 here. You guys just sort of slowly walk your way through. I need to I'm just gonna pop over right here. Okay, you guys just slowly walk through to just walk onto the other side. Just walk, it's okay. Slowly. This is what happens at low intensity exercise or at rest, like what you guys are doing right now. We've made just walk through, okay? You don't actually have to bump into anyone. We could imagine the scenario, right? There are a few pyruvate molecules that are coming through. You guys just swap sides, okay? There's a few pyruvate molecules that are coming through, okay? The most likely scenario for each pyruvate molecule is you will bump into a PDH enzyme but there will be a few that will bump into an LDH enzyme. Okay? So at rest, remember I said, all reactions happen all the time. So a few of you guys will may be made into lactic acid. The majority will be turned into acetyl coenzyme A and go into the Krebs cycle. Okay? That's what's happening. Okay. Now, as exercise intensity increases, and I just want what we're going to do. I had this in my head. I don't know if it's going to work. Okay, but you guys are here. We're going to just start having all of you guys walk through and go this way and then just loop back around. You guys go this way, walk on the other side, and go around like so. We have gone from rest, okay, to walking. So we had 3. You guys start going again. A little faster. Give me 2 more. Give me 2 more. Okay. There's more going through. More. There we go. Easy. There we go. More going through. The more that go through, the more that will get made into lactic acid and the more that will go in the Krebs cycle. Now we're jogging. So just roll with it. Just come on. Just keep crossing. Let's go. Let's go. Come on. Fast. Quickly. Here. Okay. Here. Good. Faster. Okay. There we go. Well, keep it coming. Just loop back, and then when they go back. Okay. I should have made y'all like that. Oh, now we're getting backed up. Ooh, this is a problem. Okay, now we're getting backed up. Yep, y'all just keep it going. This is carbohydrate metabolism right here. This is it.
There you go.
Okay. All right, y'all go back to your seats. Thank you.
Really knocked her back after I'm on the opposite side of where I sit. Yeah.
Okay. I hope that worked. I had that somewhat harebrained idea in the car this morning. Okay. But this is how metabolism works. All right. We are feeding carbohydrate. We are feeding glucose into the cell or out of glycogen already in the cell, and it's running through glycolysis. Okay. And as long as there's just a little bit of glucose coming through, we make a little bit of lactic acid. We make proportionally more stuff that goes into the Krebs cycle. However, as more and more glucose gets fed through the system, we still have a bunch that goes into the Krebs cycle, but we start making more and more lactic acid simply because as more glucose comes through, there's still always, we can calculate whatever our probability was. What's 2 and 7? It's like, it's like 28% or something like that out of all of those things. Okay, probably a little more than that that come through there. Okay, and so that's what happens during exercise. At rest, there's a small amount of glucose coming through our cells. As you go to walk, we start sending more and more through. As you jog, more still. When we sprint, you jam a bunch through, but then the time becomes a little bit of an issue. Okay, but that's what's happening here. And again, it all comes back to the random interaction of glucose hitting the things to get shot down to pyruvate. And then as the pyruvate moves through, is it more or less likely to bump into LDH or PDH? Okay. And that's going to send us where we want to go here. Right. The thing that we will talk about on Friday is there's some stuff going on over here that even though sometimes the pyruvate interacts with PDH, it can't all make it over here. Okay? All right, good deal. We'll see you guys on Friday.